Common mode response. An important attribute of differential amplifiers is their ability to suppress the effect of common mode perturbations. Example portrays an idealized case of common mode response. In reality, neither is the circuit fully symmetric nor does the current source exhibit an finite output impedance. As a result, a fraction of the input Cm variation appears at the output. We first assume the circuit is a symmetric, but the current source has a finite output impedance. RSS figure A, as V in Cm changes, so does Vp, thereby increasing the drain currents of M1 and M2 and lowering both Vx and Vy owing to symmetry. Vx remains equal to Vy, and as depicted in figure B, the two modes can be shorted together since M1 and M2 are now in parallel, that is, they share all of their respective terminals. Here you can see the figure A differential pair sensing Cm inputs, B simplified version of A, C equivalent circuit of B. Circuit can be reduced to that in figure C. Note that the compound device M1 plus M2 has twice the width and the bias current of each of M1 and M2, and therefore twice their transconductance. Cm gain of the circuit is thus equal to AVCM equal to V out by V in Cm is equals to minus RD by 2 by 1 by 2 Gm plus RSS, where Gm denotes the transconductance of each of M1 and M2 and lambda is equals to gamma is equals to 0. What is the significance of this calculation? In a symmetric circuit, input Cm variations disturb the bias points, altering the small signal gain and possibly limiting the output voltage swings. This can be illustrated by an example. The foregoing discussion indicates that the finite output impedance of the tail current source results in some common mode gain in the symmetric differential pair. Nonetheless, this is usually a mirror concern. More troublesome is the variation of the differential output as a result of the change in V and Cm and effect that occurs because in reality the circuit is not fully symmetric. That is, the two sides suffer from slight mismatches during manufacturing. For example, in figure A, RD1 may not be exactly equal to RD2. We now study the effect of input common mode variation if the circuit is symmetric and the tail current source suffers from finite output impedance. Suppose, as shown in figure, RD1 is equals to RD, RD2 is equals to RD plus delta RD, where delta RD denotes a small mismatch, and here you can see this figure, common mode response in the presence of resistor mismatch. The circuit is otherwise symmetric. What happens to Vx and Vy as V in Cm increases? Since M1 and M2 are identical, ID1 and ID2 increase by Gm by 1 plus 2 Gm RSS delta V in Cm, but Vx and Vy change by different amounts. Delta Vx equals to minus delta V in Cm into Gm by 1 plus 2 Gm RSS RD. Delta Vy is equals to minus delta V in Cm into Gm by 1 plus 2 Gm RSS into RD plus delta RD. Thus a common mode change at the output. Thus a common mode change at the input introduces a differential component at the output. We say the circuit exhibits common mode to differential we say the circuit exhibits common mode to differential conversion. This is a critical problem because if the input of a differential pair includes both a differential signal and common mode noise, the circuit corrupts the amplified differential signal by the input CM change. The effect is illustrated in figure. Here you can see the figure effect of CM noise in the presence of resistor mismatch. Figure CM response with finite tail capacitance. In summary, the common mode response of differential pairs depends on the output impedance of the tail current source and asymmetries in the circuit manifesting itself through two effects. Variation of the output CM level in the absence of mismatches and conversion of input common mode variations of differential components at the output. In analog circuits, the latter effect is much more severe than the former. For this reason, the common mode response should usually be studied with mismatches taken into account. How significant is common mode to differential conversion? We make two observations. First, as the frequency of the CM disturbance increases, the total capacitance shunting the tail current source introduces larger tail current variations. Thus, even if the output resistance of the current source is high, common mode or to differential conversion becomes significant at high frequencies, shown in figure. His capacitance arises from parasitics of the current source itself as well as source bulk junctions of M1 and M2. Second, the asymmetric in the circuit stems from both the load resistors and the input transistors, the latter contributing a typically much greater mismatch. Let us now study the asymmetry resulting from mismatches between M1 and M2 in figure A. Owing to dimension and threshold voltage mismatches, the two transistors here you can see the figure A differential pair sensing CM input, B equivalent circuit of A carry slightly different currents and exhibit unequal transconductances. To calculate the in from V in CM to X and Y, we use the equivalent circuit in figure B. ID1 is equals to GM1 V in CM minus VP and ID2 is equal to GM2 V in CM minus VP, that is GM1 plus GM2 into V in CM minus VP RSS by RSS is equals to VP, and VP is equals to GM1 plus GM2 RSS by GM1 plus GM2 RSS plus 1 V in CM. Now obtain the output voltages as Vx equal to minus GM1 V in CM minus VP RD is equals to minus GM1 by GM1 plus GM2 RSS plus 1 RD V in CM, and Vy is equals to minus gm2 v in cm minus vp rd is equals to minus gm2 by gm1 plus gm2 rss plus 1 rd vn cm. The differential component at the output is therefore given by Vs Vy minus Vy Vx minus Vy is equals to minus gm1 minus gm2 by gm1 plus gm2 rss plus 1 rd v in cm. In other words, the circuit converts input cm variations to a differential error by a factor. Here equal to ACM minus DM equal to minus delta GMRD by GM1 plus GM2 RSS plus 1, where ACM DM denotes common mode to differential mode conversion and delta GM is equals to GM1 minus GM2. For meaningful comparison of differential circuits, the undesirable differential component produced by CM variations must be normalized to the wanted differential output resulting from amplification. We define common mode rejection ratio CMRR as CMRR equals to mod ADM by ACM minus DM. If only GM mismatch is considered, the reader can show from the analysis of figure that mod ADM is equals to RD by 2 GM1 plus GM2 plus 4 GM1 GM2 RSS by 1 plus GM1 plus GM2 into RSS, where it is assumed V in 1 is equals to minus V in 2, and hence CMRR equal to GM1 plus GM2 plus 4 GM1 GM2 RSS by 2 delta GM, similar to GM by delta GM into 1 plus 2 GM RSS, where GM denotes the main value, that is GM is equals to GM1 plus GM2 by 2. In practice, all mismatches must be taken into account. Thank you.